Hello everyone, this is Dr. Brian MacDonald, author of Practical Stress Analysis with Finite Element Analysis, and this is the second in the series of videos entitled FEA101, in which we are going to cover the basics of finite element analysis. So in the last video we introduced the finite element method and we attempted to answer the question, what is finite element analysis? So let's just do a quick review of the last video. So what is FEA? Well, we said that the finite element method is a method that can be used to obtain approximate solutions to problems in the engineering and sciences. And we said that the application of the finite element method to solving these kind of problems is called finite element analysis. So these problems are usually defined in terms of a set of partial differential equations. And it's usually not possible to solve these problems directly, so a numerical method such as the finite element method must be used. And again, if you recall, we said, well, we can solve these partial differential equations for simple problems like squares or triangles or rectangles, but if we have anything more complicated than that, it becomes very, very difficult to solve those partial differential equations. So just as an example of what those partial differentials equations are here they are expressed in terms of relating displacements to forces. So we talked about these in the last video. And here is an example of applying the finite element method to solving these kind of equations. So in this case, we were looking at a very flat plate that was held at these 2 points here and had a load acting down on this other hole here. And we applied the finite element method to that, and we solved it to find out the displacement of the plate, and then we could further interrogate those results to find out things like stress and strain in the plate. So essentially, as we discussed the last day, the way the finite element method works is it still solves those partial differential equations on very simple shapes. So in this case, we've broken up the plate into lots of simple squares and quadrilaterals. We solve the partial differential equations for each of those little squares, quadrilaterals, and then we use some complicated mathematics to essentially glue all those answers together to give us an approximate answer for how it will displace due to the applied load, and again, approximate answer for the stress or strain distribution in that plate as well. So moving on to today's topic then, why do we need finite element analysis? Why is it so important in modern engineering analysis, the applied sciences, and in product design? So much as we did the last day, we're going to take a kind of a simple example and use that to illustrate why exactly we need finite element analysis and show some of the problems that finite element analysis solves and how it helps us to optimize things. So today we're going to be looking at a steel beam which is cantilevered into a wall. So what that means is we have this steel beam here. It's got a rectangular cross section. It's 1 meter long. We're told it's 0.1 meter across, and it's got a height of 0.05 meters. It supports a 5 kilonewton load. That's 5,000 newtons at its free end. And the opposite end here is buried into a rigid wall. So it's embedded in the wall there, and essentially that end here cannot move. So we're asked some questions about this. What is the maximum stress in this beam? Where does it occur? And has the beam experienced yield or failure? So luckily we have a equation available to us, the Bernoulli beam bending equation, which helps us to answer some of these questions. And you may have come across this beam bending equation before, but essentially it says that stress in the beam is equal to the bending moment times distance from the neutral axis divided by the second moment of area of the beam cross section. So we can go and work out those items there on the right hand side of the equation. So for the bending moment to be maximum, it's going to be at the greatest distance from where the load is applied. So remember, moment is force times distance. So if we have the maximum bending moment will occur at the root of the beam here, which is furthest away from the load application. So if we took, for example, the bending moment at the midpoint of the beam, it would be 0.5 times 5 kilonewtons, whereas down here it's 1 times 5 kilonewtons. So that tells us that the maximum load, according to this equation, will be at the beam root. So we're going to take that, we're going to say 5,000 times 1, which gives us a bending moment of 5,000 newton meters. Again, if we're looking for the maximum stress, it's going to be either at the top surface or the bottom surface of the beam. So it's going to be whatever value maximizes y here. So in this case, y is measured from the neutral axis, which is at the centroid of the beam. So y is equal to h over 2 or minus h over 2 will give us the maximum value. So I'm just going to pick h over 2, which is the top surface of the beam, and I'm going to look at the tensile load. The tensile stress. So in this case, h over 2 is 0.05 divided by 2, which is 0.025 meters. And the second moment of area for this beam cross-section is very simple. It's the breadth times the depth, BD cubed divided by 12, which in this case works out to be 1.0416 by 10 to the minus 6 meters to the power of 4. So again, we'll maybe talk about this in another video some other time, but the second moment of area is essentially a measure of how much mass is distributed from the centroid. So this beam cross-section has a relatively small second moment of area. If we had something like an I-beam cross-section, it would be much larger than this, because it would have more mass located further away from the beam centroid. So we put all these into our equation, and we end up getting that stress is equal to 120 by 10 to the power 6 pascals, or 120 megapascals. Okay, so we've answered the first two questions. What is the maximum stress in the beam? It's 120 megapascals. Where does it occur? It occurs at the beam root. So the next question we need to ask then is, well, what about failure or yielding? So we've worked out that our maximum stress is 120 megapascals, but what does that mean? Does that mean it's yielded? Does that mean the beam has failed? How do we know that? Well, what we can do is we can go to a book of tables and we can look up the yield stress for this beam, or we could do some material tests and find out what the yield stress for the material that makes up the beam is. So in this case, we're going to assume that the yield stress is 250 megapascals. Okay, so now we're going to define something called the factor of safety. I'm going to say the factor of safety is the material yield strength divided by the design load. So in this case, our design load is 120 megapascals, and the material yield stress is 250. So we get a factor of safety of 2.083. And essentially what that means is our maximum stress that we worked out is about half the value of the material yield strength. So we can say with reasonable confidence here that this beam, given the conditions that we've outlined on the previous slide, will not experience yield due to the applied load. So let's just take a look at what we did in terms of a flow chart and look at the process that we went through there. So we had a candidate beam design, which was essentially the problem shown on the previous page. So again, maybe just to look back there, here's our candidate beam design. We said, well, we have a beam with these dimensions made out of steel with a 5 kilonewton load on there. So that's our candidate beam design. We did an analysis on that, and we determined the maximum stress using the Euler-Bernoulli beam bending equation. And then we got an answer there, and then we asked ourselves the question, well, is the maximum stress greater than the material yield stress? In this case, the answer was no. So we said the beam design is viable, and we calculated the factor of safety as we did here. If the answer here was yes, then we'd say that, well, yielding has occurred, and what that means is permanent plastic deformation has occurred. So we need to go and redesign the beams. We need to change something to try and reduce the stress in the beam. So we might, change the cross section. We might change the length. We might change the load, something like that. So that's just a very, very simple example, and this shows the flow chart we went through doing that example. So that's all very well, and everything went okay there. So what about a more complex problem? So what about if I took the same problem, still a steel cantilever beam attached to a rigid wall supporting a 5 kilonewton load, but now I have the beam with a different cross section, so it's got an I cross section. That's not particularly a problem, but now it's tapering in both directions. Now it's got holes through the cross section here. It's got holes through the flanges up here as well. Now what's the maximum stress in that beam? Okay, so does our beam bending equation take account of those holes? No. Does it take account of those tapers? No, it doesn't. So now we're faced with a problem. So our previous equation does not take account of the taper in the beam, does not take account of the holes in the beam. So what do? We're faced with a difficult situation. So how do we get around this? So the answer is we introduce the factor of safety into our design process to attempt to take account of the simplifying assumptions that we've made. So in other words, we're going to still use that same beam theory we had before, but we know that that beam theory doesn't take account of the taper or the holes. So we're making a lot of simplifying assumptions. So because of that, we're going to scale our answer essentially. So if our beam now, if our analysis tells us again that still it's 120 megapascals as the maximum stress, we're going to maybe divide that by 2, and we're going to say, well, actually no, or sorry, multiplied by 2, we're going to say, well, actually no, it only can take half the load that we originally thought it could because we made so many assumptions. So if we take a look at the process that we're going to use here, so here's our original process where we had a simple problem, we used simple theory and we got a solution. Now we've got a complex problem. We make simplifying assumptions that allows us to still use our simple theory. We get a preliminary result, and then we apply a factor of safety to that. So let's say our preliminary result tells us that the maximum load the beam can withstand is 100 newtons. What we would do is we'd apply a factor of safety. We'd divide that by 2. We'd say, well, actually, if we were going to give this beam to a customer, we'd say, well, no, actually, you can only apply 50 newtons to that because we've made so many assumptions. We're not confident it can actually carry that 100 newtons. So this shows the overview here of the simple and the more complex problems. The augmented design process, which we described here, where we use the factor of safety, was used for many years to make many amazing designs. So in the Industrial Revolution, it was used to make all those amazing bridges and steam engines, and it worked very, very well. The only problem with this is that it results in what we call over-designing. Okay, so if you take, for example, the previous example where I said there that we assume that our beam, our calculation tells us that our beam can take 100 newtons, and we divide that by our factor of safety of 2 and say, well, actually, no, when we're giving it to the customers, we're going to take 50 newtons. The reality is it's probably somewhere in the middle there. It's probably, maybe it can take 75, maybe it can take 70. So by saying that it can only take 50, the beam is probably, beefed up a lot more than it actually needs to be. And we could possibly, improve that design by removing some material or changing the geometry or something like that, which would save us money and allow us to make more profit in selling that to our customer. So this is what we mean by over designing. Okay, the beam is probably better than it actually needs to be in using this methodology here. So how can we improve this? Well, one of the obvious things we can do is the first thing we can do is make prototypes. So we can reduce over designing by testing prototypes. So here let's look at a flow chart of doing that and applying that kind of method. So again, we have our problem. We use our simple theory as before with the factor of safety, and we get what we call a candidate design. So we have that candidate design then, and we make a prototype of that design. Then we do an experimental test on that prototype, and we see if it passes that test. So if the test is successful, we go, well, okay, we've got a viable design and we can maybe go into production with that product, or we can do some further optimization on it if we want. If it's not successful, then we need to go back and change the candidate design, make a new prototype and test that. So in many cases, we'll end up going around in this loop quite a lot. Okay, so maybe our first candidate design is quite rough and ready because we've used this simple theory. We make the prototype, do some tests and find out it fails miserably. We beef it up a bit, we make a new prototype, again test it, it maybe fails not so bad this time. So we may end up going around this cycle a few times. So this is known as a build and break cycle because we're building prototypes and breaking them. In other words, testing them to destruction and seeing how they behave. So we can end up, as important point here, we can end up going around and around here quite a lot. And it's, we're building a lot of prototypes, we're testing the prototypes, we're redesigning, rebuilding, so we're wasting a lot of resources by going around and around in a circle here. So if we take a look then at how development costs go throughout that process. So if we look here at the blue graph, and this is development costs, so they start off low, we have a design concept. But they rise very, very quickly because we have to make our prototypes. We make our first prototype here. So we need to pay people, technical people who operate machines or whatever it is to make those prototypes. We need to pay people to test the prototypes, to operate machines, operating test machines, gather the results, so on. We need to pay for the electricity to run those machines. We may pay for materials and so on. So our costs rise and rise and rise here until we get to the end of the testing process and near production. So when we get down here and we finally have a viable design and we can go to production, our costs have risen quite significantly. If we then take a look at the green graph here shows, or the green line shows us the designer's understanding of the product behavior. So at the start of the process, the designer's understanding is quite low, and we build the first prototype, and after that it starts to rise. But the more and more prototypes you test, the more you learn about the product behavior, and the more you see what the key points are in the product, and maybe the stress concentrators, the things that are causing it to break, and you understand those. You need to understand that that's an area that needs to be beefed up more. So it's only towards the end of the testing cycle that you know an awful lot about the product and how it behaves. So there's a big gap here between development costs and the understanding of the product behavior. And that's the key point here when we're doing the build and break cycle. Costs are high early on, and knowledge of the product behavior is low until later on in the process. So if we now just try and summarize the previous slides, well, what have we said? Well, we said traditional design processes are limited to relatively simplistic equations and or design guides. We can improve these design processes by making assumptions and using a factor of safety. And we can further improve our design by building and testing prototypes. This process is expensive and takes a long time to understand how the design behaves. So there must be a better way. And there is, and it's finite element analysis, and that's what this short course is about. And as we talked about last week, we can use finite element analysis to model the way real-world processes behave and make assumptions about the way real-world processes behave. So FEA improves the design process by using what's called virtual prototyping. So let's take a look at this. So here's a flow chart showing how FEA would work. So again, we have the design problem. We still would use our simple theory and factor of safety to get us a candidate design, but we would then build a finite element model of that candidate design, and we would solve that finite element model, and we again would look at the results and we ask ourselves, well, are they acceptable? If not, we can change the design on the finite element software. So we can change the CAD model essentially, do a new finite element analysis, solve that. Again, if it's not acceptable, easily change the CAD model. So we can end up going around and around in a circle here. But in this case, it's called virtual prototyping because it's done on a computer. We're not building a real prototype. When we finally get somewhere where our results are acceptable, then we have a viable design which we always verify using a physical prototype. So even at this point, we will always build one physical prototype, hopefully just one. It could end up being more than one. And then we get on to our production or further optimization. So instead of a build and break, now we have this cycle happening on a computer and we're changing the geometry or whatever of CAD models rather than building new prototypes. Now if we now go and compare the understanding of product behavior and development costs for a virtual prototyping or finite element analysis design process, it looks like this. So our development costs are low, and they only rise as we get towards using the verification prototype, which is this bit down here. So again, why are development costs low? Because we're normally just working on the computer. We're not building physical prototypes. We don't have to pay skilled technicians to build them. We don't have to pay people to carry out the experiments. We don't have to pay for materials. We don't have to pay the power costs of running machines and so on. So we're doing it all on the computer. This could just be one engineer working on a computer. It could be a team of engineers working on a computer. So again, our costs are relatively speaking much lower than they were beforehand. And if we look at our understanding of the product behavior, so you as the designer doing FEA, because you are running so many prototypes and changing the CAD model, and it's so easy to do this, well, relatively easy compared to building prototypes, you learn a lot about the behavior of the product really early on. So this graph is almost a flip of the previous graph. In this case, our development costs stay low, and our understanding of the product behavior is high early in the process. It's only later on in the process that our development costs get high. So it's almost the exact opposite of what we had before for the traditional build and break cycle. So just a quick review then of this video. So we're trying to set the scene here for a lot of the subsequent videos, trying to explain, well, why do we need to use finite element analysis? Why it is important? So the finite element method, as we said the last day, can be used to obtain approximate solutions to problems in the engineering and sciences. We need this method because many real-world problems are too complex to solve with traditional analytical methods. If we do use traditional methods, then we must use a factor of safety to take account of our assumptions. This will often result in over-designing, wasting materials, and elevating costs. FEA allows us to test and analyze designs virtually before building physical prototypes, and this saves significant time and money by identifying potential issues early in the design process. FEA can also help us to optimize designs for performance, durability, and efficiency. So again, that's coming more into this part down here, which we haven't talked about too much in this video, and we'll talk about in a subsequent video. So that's the end of this video, and in the FEA 101 series, why do we need to use FEA? So hopefully you found this useful, and I'll see you in the next video.